Bonjour César,
Bonjour.
comment est-ce que vous avez fait votre login? Car vous êtes modérateur ici, je vois.
Je suis passé par Blackboard, comme d'habitude.
Via le link,
Oui,
juste le classroom entier. Ou est-ce que vous avez pris en link?
le link qui a été posté sur Blackboard hier.
Ah, c'est bizarre.
Je vais réessayer.
Non, 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 pas de souci, hein, bon, j'ai aucun problème. Aussi longtemps que tu me laisses faire.
Pas de problème.
Ok, pas de souci pour moi, mais c'est bizarre. Mais ça veut dire que ça réussit pour les francophones quand même à joindre. Okay, I will start my introduction. In the meantime, all the others can join as we will, according to the last updated version, we have to start at 1:30 instead of 1:15. So I will start now. The course is in English as we have a mixture of the Dutch and French speaking people. For now, it's only nautical sciences, as from next year onwards, we have mechanic engineering as well joining us here. So it means that we have quite some people around. Unfortunately, COVID is still not really friendly for me because I intended to adjust a bit the approach of this course for this year, but it will have to be postponed for next year as we have to teach online. So I cannot divide you into groups to work on exercises on site, and I can help you all out because it's of course okay. You can divide in groups online, but making exercises in groups is not easy. So we'll have to wait for that version of the course for next year because if I recall good, the 3 first weeks of this module is online, so which implies the 3 courses that I'm giving in ship construction too. So I will help you out as much as I can with the philosophy, the approach of the exercises that you will have to do in ship construction too. The exercise itself you will have to make at home. Yeah. Additional to these 3 courses, if necessary, I will make sure that we have an extra course, hopefully at school, then to help you out with exercises for those who really struggle. And this interaction that we have now will not be sufficient. There is quite some links available on the internet that will help you out with the exercises as well, which are a bit of a similar case. But nevertheless, of course, if you need extra contact, we will make sure that that is possible in the future. But okay, first things first. We'll see if I can help you out as much as I can with the exercises now, just guiding you through the philosophy and the approach. Yeah. I incorporated for today also some little videos. It's the entire video is available on the internet. It's what I gave the link as well to the students last year. I incorporated it in little pieces in this course today because if you hear somebody else speaking about a topic, it's always good than only my voice and my interaction. So the approach of a third party might be helpful in explaining as a tutorial, of course. The links I will send separately as well on Blackboard later on, but we will start first with the course of today. Oy. Yeah, I'm working on two screens, so if you see me hopping, coming and forth on the video screen, that's why I'm working with two screens. I have to because otherwise I don't see the chats appearing. So I took a shared screen uh, on another computer. So the feedback moments is following the proclamation because you have the examination at the end of the year. I know we have the courses now, examination end of the year. It seems like to be a bit of a gap, but I think it's necessary to give you all the time to make the exercises at home because you do have a lot of homework. So it's a course with less contact hours, but with a lot of points in a way that hours that you will need to do. So a lot of hours you'll have to do at home. But I'm always available, of course, for questions. Please try to anticipate and try to make the course, the exercises at home, yeah, that I'm trying to teach you now. So you have your questions prepared for the next course, which is always better to ask your questions in front of everybody because everybody will learn from your questions. Be sure that if you have a questions, most of the people have the same question somewhere, one or another. So it's always good for the other ones to hear your question as well. Uniform mandatory, you know that in the meantime, but of course it's online, so I don't see you, so you can wear whatever you like. But once we're back into school, then of course it will be uniform mandatory, which is not allowed on the exam. But in the meantime, for me, it's watches, telephones, and all those other tools. I'm not gonna check all your phones. You have to know that it's not allowed to take along, and that's it. What do you need is a pen and a calculator. For the calculator restrictions, I do follow mathematics, so it's the same restrictions as they apply. It's the same with me. So I might reset calculators, might not, depends on, but it's exactly the same as mathematics. Yeah. Reference books are available. There is a text document as well that comes along with this course. On Blackboard, you will find, besides this presentation, you will also find a Word document. And in that Word document behind, you have some extra exercises. I added already some extra ones. So for those who followed the course last year and unfortunately have to follow it again, I already made some extra exercises at the end and added onto the Word document. So you have quite some exercises available to practice yourself. Yeah.
Yes.
Yes, Loic, I heard that. Very good. Yeah, I can see who puts on the mic, so you can't do it in secret. Um, the extra exercises, of course, I give you also some tips on the solutions. Not all solutions are perfectly there, but you have enough information to come to a good conclusion. If nevertheless you have any problems, do not hesitate to send me an email or to ask to make a revision or an extra course. I hope so at school, and that we can do it even in next module, perhaps as a recap. But okay, it will only take place with your input. If you're not asking, I will not organize. I will only organize when there is a question from you as a student. Reference books are available. There are quite some reference as well in the Word document that is available on Blackboard. So there are a lot of books available also in the library that you can consult. There's a new book used by the professors of stability. That's a good start as well to use as background, and it gives a good idea. It can only help you to understand what we're talking about. Um, but that's a bit up to you. So there's, yeah, it's a bit of homework. I will just guide you through the philosophy, the principles, and you have to do it at home. Yeah. So what we will see with me, the first three lessons will be forces on a ship's hull. So it will be shear forces, bending moments, which you're already aware of, ship construction 1. We will do some simple beam calculations. That will be for today. Next week, we will go to a more block type of a vessel, calculating shear forces and bending moments. so like a ship on a simple beam principle. Then we will do at the last course with me, you will do translation from all those forces to stresses, because you know that we are not allowed to cross the yield stress. You might still be aware of that terminology somewhere from last year. If not, please revise if it's not clear what it is, a yield stress. But you have to stay below yield stresses to keep your vessel intact. So you can only work within the elastic region of your material. So you need to have an idea of the stresses. Yeah. So the naval architect will not give stress limits to a captain that he is not allowed to cross, but he will express it in shear forces and bending moments. But as you are here for an academic program, you need to know a bit more than just the basics, which means that you need to know what's behind shear force and bending moments, and that the architect will do the translation for you to stresses, and he will only give you limits for shear force and bending moments, which is quite easily to reason and to calculate in a way. Yeah. Um, the last course is a 3-hour part. It will be a seminar by Mr. Hagen. You know him already from Ship Construction 1. He will go a little bit more in detail about ship resistance. So the propulsion power, towing tanks, relations, power, speed that he will teach to you. Uh, as Ship Construction 1, upon the examination, you will have 2 parts. One part from me, one part by Mr. Hagen. The examination is 2 hours. You will need them. So it's a warning in a way that you really have to have exercised at home. You need to know the exercises. You need to know the approach. If you have to study upon the exam, you will not have sufficient time. So those who are well prepared, who know the exercises, I already had 2 years ago, a student had 20 on 20. It's just everything is correct. Everything is correct. No problem. You get 100% of the points, and it is possible, but you need to be prepared. If you come unprepared and say, oh, we'll see what I know, you will not get there, because 2 hours, you need 2 hours for the examination. Okay, you do need them. So it's just a warning in advance. So you really have to make all the exercises by yourself. If you have solutions from previous students from the last years, good, keep them at hand, but don't use them in a first instance. Make it yourself. Use the solutions as checks. Yeah, but make it yourself. It's such a world difference in just reading solutions from others and doing it yourself. The only thing that I can give you, it's up to you to do it, not up to me anymore. Okay. The fourth course, which will be given by Mr. Hagen, it's a 3-hour course, so do not forget it. It's 13:15 to 13:30. I forgot to change the hour here, the timing. But I hope it will be in school. We'll see, depending on the COVID restrictions from the school, if it still be online, yes or no. Okay, but now, okay, unfortunately it's online because I do not like really online for this course, but okay, we will manage. Last year, there were quite a lot of people who succeeded. I think a lot of people succeeded for the course, meaning that if you try at home, that it is possible. It's more than possible, huh? Because there were quite some good succeed percentage of the students last year. So it means you're getting used to this type of exam, and knowing what exercise you have to do means also that there's a lot of distribution amongst all of you about solutions and exercises, which is very good. Yeah. Okay, so a vessel's hull has to endure forces coming from outside, of course, and also coming from inside, meaning the static forces, which is just the weight of the vessel, the weight of the cargo, people on board. It's all considered as being static forces. Dynamic forces is all the outside forces, wind, sea state, all those things is considered as being dynamic. Yeah. Besides the normal forces, of course, there are exceptional forces like impact, damage, overloading, which is not normal and is considered as exceptional. A naval architect will take it in consideration until a certain limit. Okay. Explosions he can't take into consideration. It's not normal to happen. And if it happens, yes, okay, you have damage. That's normal. But the naval architect will take for sure into consideration all the normal forces that your vessel has to stay rigid, intact, a part of exceptional forces to a certain level limit, not further than that. Normal forces, static forces, you'll know, as I told you before, is the weight distribution. Your weight is up to now, for sure, taking into account transverse stability as you already had, takes into account one vector. So all the weight is taken as one single figure, one vector taking place in the center of gravity of your vessel. Nice for stability purposes, but when it comes to shear forces, bending moments, forces leading eventually to stresses on your vessel, we want another approach. We will look at the distribution of that vector along the length of your vessel. So you see here the distribution along the length of your vessel is not the same up front as at the back. So it's like a bit of a mixture of high and lows over the entire length of your vessel. What is the total weight? You should know it. Light weight, dead weight, low displacement, light ship plus dead weight. In case you still have problems with it, please do not hesitate to contact me, but you have to know this. Yeah. And throughout one of the exercises, it might really be useful to have an idea about this. What else is working on your vessel, seeing as being a static force? Is a buoyancy force. Your vessel, as you know, is not sinking, is not flying, meaning it's being carried by a certain reaction force, which you can see as the Archimedes force, or the buoyancy force. Up to now, same story. You saw it as one vector of which the height is equal to the displacement of your vessel. Water displacements of your vessel, which is eventually equal to the total weight of your vessel. This vector has not the same point where it applies. The weight of your vessel takes place in the center of gravity, the total weight, like my total weight, I also have somewhere a point of gravity in my body where it takes my vector of my total weight. When it comes to the buoyancy force, the Archimedes force, it takes place in the center of gravity of your underwater vessel. Why? The Archimedes principle, Archimedes force, equals the weight of the displaced water. The weight of the displaced water equals, that you should know and is very important, is the underwater volume of your vessel multiplied by the density of the water. So your underwater volume is representative for the buoyancy force. So is the center of gravity of your underwater vessel, which is the reference point for your buoyancy force. 2 points, stability. That's it. That's stability. And it gives you a moment and you capsize or you do not capsize. You have a positive or a negative stability. Simple as that. Actually, stability is not really difficult if you understand the principle. Yeah. Again, this is not what we are interested in. We look at the buoyancy force distributed over the entire length of our vessel, like this. So we have a static weight downwards distributed over the entire length. We have a buoyancy distribution over the entire length. If I would do the sum of all those surfaces that you see here for weight and buoyancy distribution, what would be the result? The total sum of the weight distribution and the buoyancy distribution. What will be the sum? If you sum it up, is 0. Your vessel is floating in the water, so it means that they're equally in height. So if you take the resultants, they're the same. Otherwise, your vessel would be flying or sinking, and it's not the case. Hopefully, it will float in the water. But if you look along the length of your vessel, then you see that the resultant be positive areas. Oh, let me look here. You have positive areas here, down, You have negative zones and positive zones. Yeah? The sum of it is 0, but it's distributed along the length with positive and negative parts. Yeah? And that is now the reason why we have shear forces and bending moments due to the static forces of your vessel. Yeah? An empty vessel, as you will know, yeah, weight distribution of a minimum ballast condition. Ballast condition is an empty vessel, meaning that all the ballast tanks are filled with water to guarantee a certain weight, a certain minimal stability in a way. Yeah, it means that in that way your vessel is tend to hog, and with a vessel tending to hog, you see that the resultant forces are more positive in the middle and more negative at the backs. Yeah, and your vessel is doing like this. When your vessel is fully loaded, you just have the opposite, and your vessel tends to sag due to the static distribution of all the weights. Yeah. Beside those statics, you have the dynamics. Waves, green water, this is an example. Slamming is an example. So slamming is also part of the operation of your, as I saw, I just pressed accidentally the mute button, but just in time. So slamming is also part of it. So it means that a naval architect has to take into consideration all those forces as well, because all those forces your vessel is also exposed to and will also lead to shear forces and bending moments. Yeah. How does a architect take this into consideration the sea state? Looking at statistics. He goes to statistics and he looks at the significant wave height, not the mean height that you will encounter, not the maximum height that you will encounter. He will take the significant wave height, a terminology normally you have seen in vessels technique with Rafmeskes, I think so. Okay, so you take 1/3 of the highest waves that your vessel is designed for to navigate, you take into consideration. There the average from, that is your significant wave height. And that's a value of which the naval architect will take into consideration to calculate all the stresses that your vessel will be exposed to, dynamic sea state. Yeah, because he has to know all the stresses that you encounter. Meaning also, very important side note, that vessels are designed for certain areas to navigate. Your vessel cannot necessarily just cross the ocean, the Atlantic. If it's not designed for, your vessel will not withstand all the stresses that come along. A vessel is designed for certain areas. Normally, if nothing is mentioned, according to the Ajax, it will be in that conditions North Atlantic. When you're deviating, yeah, when you're only designed for the Canadian lakes, then it's mentioned in your class certificate. Huh? So if nothing is mentioned, normally you're designed for North Atlantic, worst case sea states. Huh? Otherwise, it will be specifically mentioned. But if something is mentioned, you must be aware that you're only designed for the dynamic conditions within those regions. So you cannot just go to across the Atlantic because your vessel cannot sustain all those stresses. It's not designed for to have that amount of stresses. And that you must be aware of. Okay, effect of the waves, I told you significant wave height will also lead to movement of your vessel, meaning stresses, eventually forces within your ship's structure. Yeah, hogging, sagging, things you know, so I will go and pass it quickly. Naval architects make use, of course, of finite elements to evaluate sea states and stress, and also in the structure. This is always done by simulations, computer-based programs, which are quite good, but it stays an approach. Huh? So it's only an approach of a simulation of the reality. You always have to keep that in mind. Meaning that we always have to take account safety margins. Naval architects take into account safety margin, meaning that you will never use a yield stress as a final limit. It also be the yield stress taking into account the safety margin. Yeah, it's very important. Things exceptional forces which normally are not taken into consideration for the merchant marine. I'm not talking about the navy, that's different, but for the merchant marine, collision, grounding, explosion, to a certain extent, but stop somewhere. There's a certain limit but it's not for full collision explosion that your vessel is designed, of course. So these are things that can happen, yeah, and that leads, of course, to damage, yeah, and that's, of course, most of the time is linked to operational errors from, let's say, the captain, because he has the final responsibility, yeah. Overloading is also something that happens, and which is a responsibility of the people on board, and which is your responsibility, and the reason why we treat it. Because all those dynamic things that I'm talking to you about, it's not within your hands. If you go navigating, you can't control it. It's the responsibility of the naval architect. But the one thing you can control is how you charge your vessel, how you distribute all the forces. And that's why it's important that we teach this towards you, and that you have an idea what's all going on and what's behind loading and discharging and shear forces, bending moment, and the stresses. Yeah. To make the calculations easy on board, you, of course, what do you have? You have computer programs who do everything for you. Yeah. Who do the work for you. Nice, easy, but you have an academic background, so you need to know what's behind it. Yeah. To make your life easy and simple, we will always compare a vessel with a beam. Right? A beam can be detailed, that you really have side shells and girders, like you will see at the end in a Word document. You will have some exercise, a new exercise for those who already follow the course, like you're really a profile of a vessel with a tank top, center line girder, you have side shells, walls with certain dimensions, and then you can do calculations. You can simplify it even further, and you can compare a vessel with an eye profile beam. Yeah, so both things exist. If you compare a vessel with an eye profile beam, then the top flange is considered as the shear strake, the top deck, yeah. The bottom flange is considered as a double bottom, and the side web is considered as the all the longitudinal things going really up and forth. So meaning the side panels of your vessel and all longitudinal bulkheads, which are quite solid up forth. That's the side web. And if you simplify it like an eye profile beam, the behavior of this beam is really comparable to the behavior of a vessel. Yeah? And that's why it's easily to use this as an example, and also in exercise, it's a nice approach to simulate what happens on board of a vessel. Yeah? So you know that a vessel bends, hogs, sags. Hogging and sagging leads to compression and tension. What you saw in ship construction 1 is that the compression and tension is the highest at the outer flanges. Huh? So if you go like this, sagging, yeah, then you have tension in the bottom, and I have in your deck compression. A vessel is not only subjected to hogging and sagging. As we saw, the weight distribution of our vessel tends to have positive and negative parts, meaning that if you will chop it into pieces, all the pieces of your vessel will have a different height in the water, will have a different freeboard. Yeah, meaning that if you glue them all together, that you will have tension and stresses and forces perpendicular to your plane. And that is the highest, the shear stresses are the highest in the middle in your web. Yeah, but that are things that we saw in ship construction 1. So it's important that you revise that part, and then you can continue, and then you really capture the entire content of what is necessary. Okay, you can just say, oh, I will just do the exercise and that's it. I succeed because Remke's part is only exercises, correct? But you will go navigate. You have quite a big of a responsibility later on board. So it's necessary that you understand the global picture. Huh? So here you see an eye profile beam, and you consider it in this case like the vessel. You neglect a bit Archimedes, and you see it as like it's carried by wave tops at the bow and at the stern. And then the total weight is visualized here as being the biggest in the middle. And it gives you indeed hogging and sagging, but also bending moments internally. What is internal, external, we'll come back to that later on. The same you go, of course, with hogging. These are all visualizations that you can use eye profile beam compared to a vessel. This is the story what I wanted to tell you about. If you look at the weight distribution of your vessel, you might weigh more at the ends and less in the middle for sure when you're empty and in ballast condition. Your vessel tends to hog. Yeah. If you chop it into pieces, what do you see? Every piece has a different freeboard. Yeah. So wait. If you look at this part and you're located here, what do you see? This part tends to go downwards. But in reality, it's all one piece. So it means that internally, you have at this location a reaction force. And that's the shear force. So your shear forces you can approach as a result from external forces, which is the weight in this case. And then internally, your material has to counteract because it doesn't want to crack. It's all glued together. And that's the shear force. Another way, you can see this pen. What does it also do? This is your person. And this is the end of your vessel. This pushes downwards. What do you see happening? You see like a moment happening. Yeah, it tends to angulate this part. In reality, it's all glued and stick together. So besides only shear forces, you also have here, this is trying to turn ourselves downwards. You will have a reaction force to counteract. So you also have bending moments to counteract the bending moments that your vessel is exposed to. And those internal shear force and bending moments, they lead to stresses, and those stresses should not be higher than certain limits. And that's actually the red line through the entire story. Yeah. Now I will show you a small part. So it's very, very small, but it's just that adds and somebody else explains you. It might be useful to hear it from somebody else. And also certainly online, we are taught, we follow courses as well. We are taught that we have to activate you, because if I'm talking the whole time 2 hours in a row, then you fall asleep. So this is considered as being an activating intermediate, how do you call that? Yeah, time zone, time frame. So let me first go to
Shear.
the correct part. Yeah, the entire video you will have to watch, but I will only show you parts of it.
When a beam is loaded, internal forces develop within it to maintain equilibrium. These internal forces have two components. We have shear forces, oriented in the vertical direction, and we also have normal forces, which are oriented along the axis of the beam. If the beam is sagging, the top of the beam will get shorter, and so the normal forces in the top of the beam will be compressive. The bottom of the beam will get longer, and so the normal forces in the bottom of the beam will be tensile. Each of the tensile normal forces has a corresponding compressive force, which is equal in magnitude but opposite in direction. As such, these forces don't produce a net normal force, but they do produce a moment. This means we can conveniently represent the internal forces acting on the beam cross-section using just two resultants. One, shear force, which is a resultant of the vertical internal forces, and one bending moment, which is a resultant of the normal internal forces. This is a very common way of representing the internal forces within a beam. Drawing the shear force and bending moment diagrams is just figuring out what these internal forces are at each location along the beam. These resultant shear forces and bending moments will depend on the loads acting on the beam and the way in which the beam is supported. Beams can be loaded in a number of ways.
Okay. Voilà. Dus that's sorry, I have to switch back to English. So this is another approach of explaining that we indeed, if we talk about shear forces, bending moments, that will eventually lead in the third course to the calculation of stresses. That we always consider the internal parts, the internal shear force and bending moments, which should not rise above certain limits, otherwise you have failure. And for sure, when you enter the plastic region zone, then it's considered as being failed, because we do not want permanent deformation. Elastic deformation is normal, but permanent deformation we do not want to reach and we do not want to obtain. Okay, how do you have to see loads in the calculations we will make? We will do simple beam calculations for today. Then you will see concentrated load of point loads. It's like, for example, a car on a deck. Every wheel will have a certain point load, concentrated load. Yeah. You will also see that we will consider uniformly distributed loads, which means, like, for instance, a tank filled with freshwater tank, which is filled with water, which means it's so many ton divided over the floor of the tank. So it's like a uniformly distributed load. The same we can translate to simple beam calculations. You will have on board, most of the parts will be considered as being either squeezed on both ends. You do not have free ends, you have to both fixed ends, but you can have also in beam calculations a free end and a fixed end. You have panels which are supported, like, for instance, reinforcements, girders. They reinforce the tank top, and then you have like supports on a, that's also possible, and that you can all simulate as well by simple beam calculations. If you look here, how to calculate those internal shear forces and bending moments, I told you they relate to the external forces, and this is a nice visualization. So you see here a beam fixed in a wall and free at the other hand. You see at the end of that beam is being pushed upwards by a certain force P. So which your beam, it tends to go upward, but nothing happens because it's in equilibrium. But that means that internally, if you're a fiber, a microbe in that beam, you have to counteract that force. How do you counteract that force? You counteract that force with a certain internal force. And then you see this here. No, I have to be here with my pen. Internal force V. For the beam to be in equilibrium, the reaction force has to be the same as the external force. So you have the internal shear force you can easily calculate on basis of the external force defined as P. What is the moment? If you're positioned in that cross section, MN, here, imagine yourself located here. Somebody pushes upwards. What do you see? This beam has a moment that tends to do this. How do you define that moment? The moment is force multiplied by arm. It's P multiplied by that distance x. Oh, here, distance x. Yeah? For your beam to be in equilibrium, that internal moment at that position where you're located, the cross section MM, equals what? P multiplied by x. It has to counteract that moment to be in an equilibrium. And that's the basics. So the external forces will determine what happens internally, what you have to counteract. And those forces moments eventually will lead to tensions that have to stay below limits that the naval architect will give you. Sign conventions, since we do exercises, of course, we need to keep up to a sign convention. We have deformation sign conventions. You can do it depending on happy phases, sad phases. Usually I use the static ones. The static ones means that everything which is tensile is considered positive, compressive is negative. All the forces acting upward is positive, downwards I consider as negative. If you go to moments, moments on the load of the beam positive and going counterclockwise, clockwise. So if you go clockwise, positive, counterclockwise, negative. In a way, you can do whatever you like with those sign conventions. Just put somewhere on a piece of paper the convention that you use and use it throughout the entire exercise. That's the most important thing. If you swap in between, your answer will be not correct. So use a sign convention and use the same approach for your entire exercise. Eventually, your result can be perhaps positive and I have negative, or vice versa. it's no problem because the absolute value is the one that is necessary to take into consideration to calculate eventually stresses. Your stresses can be tensile, can be compressive. Both should be below the yield stress. Whether we're talking about tensile or compressive, it doesn't matter. It both has to be below the yield stress. So you can, I'm not so strict in the sign convention. So positive, negative can be swapped as long as the absolute value is correct. And you can only guarantee this by using the same approach over your entire exercise. Okay? So what do you see here? To be in equilibrium, I told you the sum of the forces must be equal to 0. Yeah? But when we talk about the sum of the forces, sum of the moments equal to 0, we talk about external forces leading eventually to internal forces, the reaction forces. Now, what are also external forces? The external forces are also considered to be the forces here where your beam is carried. In this way, it's carried only by the wall. The wall will prevent your beam to move down or up. So you have a reaction force considered as an outside force upwards when your load here at the end is downwards. You have a reaction force on the wall going upwards. This moment tries to move you this way. So you'll have a reaction force in the wall because it's not happening. That reaction force in the wall is also considered as an outside force. Yeah, and the sum of all those forces has to be equal to 0. It will be one part to come to the exercises. Yeah. Shear force produced by a hog ship. Same here. Archimedes force carries your vessel, is considered as an outside force. The weight of your ship is considered as an outside force. All those outside forces leading to internal shear forces and bending moments in your vessel. Okay? And that we will eventually calculate. Yes, shear forces, bending moments, how to calculate. I will go straight first to the beam exercises and then I will come to this, or you can look at this later on, then it will become clear what it's meaning. Okay. How do you calculate shear forces and bending moments? Where this will eventually lead to a vessel. This is computer-based programming that will illustrate it on board, but you need to know the principles comparing this vessel with an I-shaped profile beam. Yeah. The importance, as I told you, is that they are linked to stresses, and stresses has to stay within limits, otherwise you have failure, and you have to stay below the yield stress, you have to stay within the elastic region. And that's the red line through all the exercises. Fixed support is one thing we saw. There are also pin support and roller supports. If you look here downwards, the roller support, let's start here. Oops, this goes there. The roller support. A roller support allows your beam to move left, right. It allows your beam to have a moment. It only restricts the movement in the vertical direction, meaning that a roller support leads to a virtual external vertical force, because that there it limits, and there you have eventually a reaction force in that support. A pin support will also restrict the movement of your beam in the horizontal plane, meaning movement left, right. So you will have, in case of a pin support, also restrictions in that level. And you have a reaction force, also considered as an external force. When you go to fixed beam supports, I told you before, you also have a moment to take into consideration, besides vertical and horizontal forces. Yeah. Why I tell you all this will become clear when we come to example exercises. Okay, a small introduction or summary in another way. Let's put it that way.
Shear force
In 50.
can be loaded in a number of ways, the most common being concentrated forces, distributed forces, and concentrated moments. Beams can also be supported in a number of different ways. They can have pin supports, roller supports, or be fully fixed, which each restrain the beam in different ways. Pin supports prevent vertical and horizontal displacements, but allow rotation. Roller supports prevent vertical displacements, but allow horizontal displacement and rotation. Fixed supports prevent all displacements and rotation. If a certain degree of freedom is restrained at a support, we will have a corresponding reaction force or reaction moment at that location. For example, rotations are permitted for a pin support, so there is no reaction moment, but displacements in the vertical and horizontal directions are prevented, so we will have horizontal and vertical reaction forces. So how do you determine the
Okay,
shear forces and bending
that's
moments
it.
within a beam?
Okay. Now, beams, of course, can have more than one support. Cantilever beam is only fixed in the wall. Fixed beams fixed on two sides. Simply supported beams, which is most of the cases that we will consider in the exercises, is like one end is freely moving in the horizontal plane and the other one is pinned. So your beam with a simply supported condition can do this and can elongate depending on the stresses and the forces which are being put onto. And that in the exercises, just to simulate what happens and what's all behind, is sufficient for now. And I only have with you 3 contact moments, 6 hours, which is not a lot. So we have to make some decisions and see what we treat and what we do not treat. Classification of beam, statically determined, see, that's what we are talking about. So your beam is in equilibrium, meaning that the moments, the sum of all the moments are equal to 0. The sum of the forces are equal to 0 in the horizontal, in the vertical plane. That's the basis to be in statically sound and statically okay. So as soon as you have some values given, you can calculate all those reaction force, you can calculate all the external forces. And in the exercise, it will be necessary to have first an idea of all the external forces that is exposed to your beam. Like a naval architect first has to be aware of all the possible external forces that your vessel is being exposed to. And then you can go and look into what happens into the structure. What are the moments and the forces in the structure itself? What are the stresses coming along? And do we stay below the yield point? That goes behind. Yeah. Okay, a little continuation.
Shear force and
One second.
So how do you determine the shear forces and bending moments within a beam? There are 3 main steps we need to follow. First, we draw a free body diagram of the beam. This shows all of the applied and reaction loads acting on the beam. The next step is to calculate the magnitude of the reaction forces and reaction moments at all of the beam supports. We do this using the concept of equilibrium. To maintain equilibrium, all of the forces in the vertical and horizontal directions should cancel each other out. Similarly, all of the moments acting at every point along the beam should cancel each other out. This gives us a set of simple equations we can solve to calculate the reaction forces and moments. If we can calculate all of the reaction loads using the 3 equilibrium equations, the beam is said to be statically determinate. For some beam configurations, like this,
And that's it. We will only do this type of exercises, yeah, where it's indeed statically nicely being able to calculate. For example, what do you see here? A simply supported beam with a weight in the middle, and it's considered as being a concentrated load in the middle with a certain force W. When you press in the middle of that beam with W, then you know that your reaction forces in your supports, roller and pin support in the vertical direction equals how many? What is R1 and R2? So if you look here, you press with a pin support W in the middle. You have here a reaction force due to the pin supports in the vertical direction. This one, where am I here? I call R1. This one I call R2. What is the height of R1 and R2? Logically, most of you will say a 50-50. Then you just divide it 50-50, which is correct if your point load is perfectly located in the middle. Then R1 and R2 are indeed correct, equal to 50%, 50%. Huh? But it's not necessarily correct. If your W, your load, is not perfectly in the middle, then R1, R2 will not be exactly 50-50%. Then the division will be differently. Now, how do you calculate this? On basis of what we just said. Yeah. So what do you know? The sum of the moments. Let me see, where am I? Here. Yeah, I have to look always. The sum of the moments. And let me take around the start of your beam about R1 should be equal to 0, which meaning that the moments should be equal to 0. So your counter moment that located there, yeah, equals what? Equals what is happening for moments at that location. W multiplied by which arm? Half of the beam. Let's say the beam has a length of L divided by 2. This is one moment. Force multiplied by arm. It acts in the clockwise direction. So we say, okay, this is a negative moment. This is the only moment when you're placed here in front of the beam that you visualize. No, you see another moment. The other moment that you see is the force R2 at a distance of L, located from you where you are standing. That are all the moments, the sum of the moments, if you're located there in the up front of your beam. Those should all be equal to what? Equal to 0, which gives you one equation. If you solve that equation, then you will get indeed that your R2 equals to W divided by 2. You can do that yourself. It's just mathematics. You should know how to solve an equation that I suppose that you know. Yeah, so try to do it yourself at home. Try to do it now. Please do so. And then you get an expression for R2. You do the same philosophy, the same approach, but then you will locate yourself at the other part of the beam. Then you will locate yourself here. Where am I? Here. And then you will look at all the moments acting upon it when you're located, positioned at the end of the beam. The sum should be equal to 0, and then you get an expression for R1. And you will see that R1 will be indeed 50% of W. Yeah? Cross-check is what? R1 plus R2 should be equal to W, because all the forces in the vertical plane should be equal to 0. And that's a cross-check that you can do. So you can easily, in the beginning of all exercises, check if you start off on the good feet. If you started correctly with the correct figures, do those cross-checks, please, if you can, upon the exam. You never know. An easy, simple fault in calculation is possible. Okay, upon the examination, will tell me, yes, madam, but you say it's possible to have a simple error in your calculation. Correct. If you have a simple error in your calculation, you will not have 0 with me, but half of the points. Okay, so that's an agreement that I make with you. You have half of the points. Is your principle, your philosophy is good, and you made one small error in your calculation. But the idea should be correct. If not, it's 0. So actually, my point giving is easy. Philosophy and figures correct all the points. Philosophy correct one simple error in a calculation. You get half of the points. All the other scenarios is 0. So if you make 4 errors in calculation, you also have 0. Okay, and that's how I reason and how I correct your examination at the end. And here you see the solution. Yeah, how you do the approach with the moments around A, the moments around B, the sum of the forces in the vertical direction. Is there somebody who does not understand this philosophy? How to calculate the reaction forces at the end and the beginning of your beam, there where you have the supports, and those are considered as external forces. So far, so good. Okay, perfect. Yeah, the same principle philosophy you will have to use, yeah, when your weight is not perfectly concentrated in the middle, but it's a bit somewhere else located, huh? Here you see an exercise in the course with values instead of x and y's and r1 and r2. You have here values, huh? What do you see with those values? The shear forces. How do you calculate them? Okay, we started by calculating the external forces here. We have 20 kilonewton, which your simply supported beam is exposed to, perfectly located in the middle, so we know that it's 50-50 division for RA and RB. 10 kilonewton on each side. And that is all external forces where your beam is exposed to. That you can calculate now. Huh? What is now the shear forces evolution over your beam? The bending moment evolution over your beam. Well, to know the evolution of your shear forces, you have to imagine that you're a micro and that you crawl into your structure. Yeah. First of all, you're located at this point. If you're located at this point, just a fraction of a millimeter before your beam, then it's 0. But suddenly, if you're here, just a fraction of a mathematically undefined distance from your start, then you see that you here have a force pointed upwards, an external force that points upwards of 10 kilonewton. That force has to be counteracted by your material in order to be in equilibrium. So that's why it's very important to make the distinction between external and internal forces. In our calculations, to look at the internal stresses, we need the internal forces and moments, yeah, which is linked to the external ones. So the internal force here has to be equal to 10 kilonewton to be in equilibrium. Now, I'm a fiber, and I'm a fiber that goes further along the beam, and I position myself here now. What is the force that I need to counteract? Again, 10 kilonewton. So it remains 10 kilonewton just up to this point. Up to this point, you will have to counteract not only 10 kilonewton, but also suddenly 20 kilonewton. So you have a drop and you go to minus 10 because 20 minus 10 is 10, of course. So if you're located here as a microbe inside your beam, you have to counteract all these forces, which is minus 10, and it remains minus 10 just up to the end. Okay, now I looked from left to right. You can also look from right to left. It will give you exactly the same, but just the sign will be different. Yeah, and as I told you before, you can neglect the sign at the end. Not throughout the exercise, but at the end. Yeah, and that's the shear forces that happens here in this simply supported beam with a weight of 20 kilonewton exactly in the middle. And that's how you draw the shear force diagram. You must be able upon the exam to draw shear force diagrams. Yeah, you must be able to reason this. Imagine yourself, picture yourself as a microbe that crawls into the beam and then see what you have to counteract. And that you need to be able to draw. It's half of the points, huh? This 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 drawing. Now what happens to the bending moments? Huh? You have that 10 kilonewton here. And now you're a bit further away at a certain distance. Then you have to have a moment that has to counteract the external moment. What's the external moment? Is it 10 kilonewton multiplied by this arm? It gives you a certain value, and that's your bending moment at that location. But as you, as a microbe, you will move along your beam, the arm will constantly become bigger, 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 bigger. So your moment becomes bigger, 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 bigger. Yeah? Until you reach a maximum. A maximum will be exactly in the middle of the beam. Why does it go downwards? Because you will pass a 20 kilonewton, which gives you another moment, huh? Because a 10 kilonewton, as you see here, acts that way, 20 kilonewton acts that way. So it will subtract, and then you will have a moment that goes downwards, downwards until you reach 0. And that's the approach of bending moments. And that's how you visualize bending moments. Yeah. And this is the total picture. Now, another approach, but explained by somebody else in case you are not yet following what I was talking about.
Shear force.
1 second. Somewhere here should be play.
Calculated all of the reaction loads. The third and final step is to figure out the internal shear forces and bending moments at every location along the beam. To do this, we will use the concept of equilibrium again. If we cut our beam at any location, the internal forces and moments need to cancel out the external forces and moments so that equilibrium is maintained. This allows us to easily calculate the shear force and bending moment at each location along the beam. All we need to do is start from one side of the beam and move the location of the cut along the beam, calculating the shear forces and bending moments as we go. Now is a good time to define the sign convention we will be using.
Okay,
Applied
then we
force.
do not need sign convention. Not for now. Okay, so you always have to look external forces will give you internal forces, and it's the sum of all the forces, sum of all the moments that you need to counteract looking from one side, left or right or left, that's up to you. Yeah, you can choose. Oops, that's not it. Here. Then you have an exercise of which you have the solution because you will have to do it at home of a point load node not exactly located in the middle, but somewhere at 2/3 of the length. You will need to calculate your reaction force. In this case, your reaction force is not 50-50%, so it will be a bit more on one end than on the other end. Following the same principle as before, calculate the sum of the moments, the sum of the moments around A, the sum of the moments around B. You come to an equation and you will find our A and our B. Exactly the same principle as before. Yeah. Okay, I will give you one more.
Shear force.
6666608 or 9.
We can then use the equilibrium equations to determine the unknown reaction forces at point A and point B. The sum of the forces in the vertical direction is equal to 0. So RA plus RB is equal to 15 plus 6. Because HA is the only horizontal force, it must be equal to 0. We also know that the sum of the moments about any point along our beam must be 0. Let's consider the moments about point B. That gives us this equation, which we can solve to determine that RA is equal to 12. By substituting RA into the previous equation, we can deduce that RB is equal to 9. Now that all of the external loads acting on the beam are defined, we can draw the shear force and bending moment diagrams. We will start from the left-hand side of the beam. Let's draw the free body diagram for a location immediately to the right of the 12 kilonewton reaction force. To maintain equilibrium, the shear force must be equal to the reaction force. We can draw this on our shear force diagram. The shear force will be constant until we reach the next applied force. The bending moment must be equal to the 12 kilonewton reaction force multiplied by the distance x to the reaction force. This gives us the equation for a straight line, which we can draw on our bending moment diagram. We then repeat the process by moving the location of our cut further to the right. This time we place the cut immediately after the 15 kilonewton force, and we draw the free body diagram again to determine the shear force and the bending moment. We repeat this process until we have covered the full length of the beam. we end up with the complete shear force and bending moment diagrams for the beam. That example was a fairly simple one.
Okay, so if we look here, yeah, on this visualization, is there somebody who noticed something? Can you relate the forces to the shear forces? Can you find a relation between the shear forces and the bending moments? Somebody who can see it? Somebody see a relation? So meaning that there might be a relation somewhere between the forces, shear forces, relation between shear force and bending moments. Something that you should see or have seen, I think, in mathematics. Integrals. You have learned integrals, mathematics. Yeah, the bending moment is indeed the integral of the shear forces. Yeah, what is an integral? An integral gives you the area underneath the curve. Very good, Samuel. So the bending moment is indeed the integral of the shear forces, but the shear forces is also the integral of what? Of the forces. If you have a straight line like 12 kilonewton, a straight line is considered as a surface. It's a value 12, and that value 12 remains the same. So at 1 meter, your shear force is still one single line. It's still 12 kilonewton. It's not a surface, it's a line. So the shear force is the integral of the forces, and the bending moment is the integral of the shear force. So if you are able to find an expression, yeah, of your forces, you can easily, by integrals, solve shear force and bending moments. And that's how computer programs do it. They will use integrals because these are very easily exercises. You do not need integrals to solve these problems, but you can if you like. Huh? So if we go to uniformly distributed loads, if you like, you can solve them by using integrals. Be my guest. As the exercises are quite simple, you can also just do it in a much more simple way. But that I leave up to you. You can do it the way you want as long as your answer is correct. Use integrals or you use a simplification as I do, up to you. Yeah, I will explain you the simplification as I know that my colleagues explained you the integrals. But as long as your solution is correct, all fine by me. Yeah. Know that computer programs use integrals, of course, because it's not that simple anymore when you go on board. So these are exercises you can easily do at home. That's a simply supported beam with one load or two loads, as we just saw an exercise, the solution you have in the Word document with the values. You saw just a nice example with the diagrams evolution. You need to be able to draw those diagrams evolutions as well. Not only values, but I need to see how it evolves, shear force, the bending moments over the length of your beam. Yeah. Now, what do you see here? The uniformly distributed load. Yeah. The uniformly distributed load. How do you calculate the reaction forces? You can find an expression for the line, make the integral of this line, and then like this, find your shear forces, make the integral of the shear forces, and find your bending moments. You can also simplify this problem, and that's how I do it. So what do you see here? You see here a uniformly distributed load, which has a rectangular shape. A rectangular shape, the surface of it is equals to what? The length multiplied by the height. The height is Q, is expressed by kilonewton per meter. So that you can suppose that Q equals 2 kilonewton per meter. Yeah. Then we can express this Q as a resultant force taking place in the center of gravity of that rectangular, which in this case is the mid of our beam. And then this is Q multiplied by L, or 2 kilonewton per meter multiplied by, for instance, 10 meter, then this is 20 kilonewton. And then you have exactly the same exercise to calculate RA and RB. It's like a concentrated load in the middle. And this is simplification you can use to calculate RA and RB. But a simplification only usable to calculate RA and RB. End of story. If you want to go to an illustration of the shear force and the bending moments, you can't use a simplification. Because as you see here, your shear force evolution at 0 start from 0 to the reaction force in RA, and then it gradually goes downwards. It's not the same as a point load as we saw before. Why? Because you have here a force that gradually becomes bigger and bigger and bigger. RA is positive. Oops, that was not the case. So you see here RA as being positive. Then you have your forces in the opposite side, negative, negative, negative. So it goes down, 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 down until the total force here equals RA. Then you get to 0. But then it goes further down. And then it goes further down up to a certain level, which I already know in advance is the opposite of RB. And then you will end eventually back to 0. Yeah? So you need to know that the shear forces is the sum of all the forces that you see, and always go back to the first illustration. Simplifications are good if you know what you're doing. Okay? Bending moments the same. You will take the integral of the bending moments, or here, what do you see? Surface positive heightens, becomes bigger, 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 bigger. Then a negative surface, it goes down, 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 and this will be the illustration of your bending moment. What you see as well, your bending moment is not linear anymore. Up to now, we only had linear illustrations of shear force and bending moments. Here it's curved. And then I need to know as well upon the exam, you need to know when your bending moment is linear along the beam or when it's non-linear along the beam. Non-linear is curved, for those who did not follow. And you can make those calculations as well. And this is an exercise where we combine the point loads with the uniformly distributed load. And I see we started at 1:30. What's the time now? 12:30 we started. When did we start? Oh, we still have time. Very good. I think I have another example. This is another exercise, but this is what I want to show you. One moment. 12.
Shear force and
1 second. Yeah, there's also an explanation with your integrals if you like, but that you will see at home. I will go straight to simplified model calculation. There you go.
here we have a cantilever with an applied concentrated moment of 120 kilonewton meters and a distributed force of 6 kilonewtons per meter. Again, we start by drawing the free body diagram. Because the support is fully fixed, we have vertical and horizontal reaction forces, RA and HA, and reaction moment, MA. Let's look at our first equilibrium equation. The sum of forces in the vertical direction is equal to 0. In this case, the only forces acting in the vertical direction are the reaction force RA and the distributed force. So RA is equal to 6 times 3, which is 18. HA is the only force in the horizontal direction, so it must be equal to 0. Next, we can take the sum of the moments acting at point A. In calculating the moment caused by a uniformly distributed force, you can remember that it is equal to a concentrated force located in the middle point of the load. This gives us MA equals 21. To calculate our shear forces and bending moments, we will start on the left side of the beam and move towards the right. This is our first free body diagram. The shear force calculation is easy, as we only need to consider the reaction force of 18 kilonewtons. The bending moment needs to take into account the reaction moment and the reaction force. At x equals 0, the bending moment is equal to the reaction moment of 21 kilonewton meters. As we move to the right, we also need to consider the moment caused by the 18 kilonewton reaction force. This gives us the equation for a straight line. We can then move our cut to the right of the concentrated moment. The moment won't affect the shear force, which will remain constant at 18 kilonewton until we reach the distributed force. But it does cause the bending moment to suddenly drop by 120 kilonewton meters. After the drop, the bending moment is again defined by a straight line. Things get a little more tricky when we reach the distributed force. We can replace the uniformly distributed force by an equivalent concentrated force with a magnitude of 6 multiplied by the length x over which the force is applied. This force is located at a distance of x over 2 from our cut. We can then calculate the shear force and bending moment equations using the normal approach. The bending moment in this section of the beam is defined by a quadratic equation. No loads are acting on the small 1 meter section to the right of the distributed force, so shear forces and bending moments in that section will be equal to 0.
Okay, so you see there are equations appearing. It's nice for those who want to do it with equations. On the examination, I will ask specific values at certain points. Yeah, and it's up to you to interconnect those points. If you want an equation to be able to calculate every little dot along the beam, fine by me. But upon the exam, I will ask you, I need shear force and bending moment values at location. Tap, 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 tap. Might be 5 points or 6 points along your beam. And I need a visualization of the evolution. And it's up to you. You can reason yourself. If it's linear, nonlinear, goes upward. If it goes downwards, you have to interconnect those points. If you really want equations and calculate every point along, fine by me. Yeah. But only thing I want is that you capture what I'm trying to teach you. So I need values at certain positions and I need to know what happens between those points. It can be a sketch, huh? I will ask you upon the examination to take two color pencils, like a marker, and you have to mark what is linear and non-linear. And then I see if you followed the content, yes or no, and what I'm trying to tell you. Okay. So far, so good. I will just explain you this one after a little break because I see we have time and I think you all need a little break as well to get something to drink or just to breathe and get some air outside, some fresh air. Just realizing now that you do have homework in making exercises. I'm sorry, but indeed you do. And then I will just make one more exercise with you today to finalize this. And this is a uniformly distributed load, which is not horizontally, but which has like this variation along the beam, which is not the same at the start and the end. And how to make this approach in a simple way. You can do it again with integrals if you like, be my guest, but I will give you within this and 5-10 minutes an approach in a simple way how to solve this problem. Okay? I'll talk to you in 5 to 10 minutes again. Okay. Questions so far? Not really. Okay, what I will do, let me see. I will take an empty sheet. Yeah, I will stop this one. 1 second. That we did saw, I guess. Yes, that we did. I want to keep this card. So I can stop sharing as well. I did. Apparently, that's good. Why I have two screens. I'll take a whiteboard. There you go. Okay. So what was the exercise? We have a, where am I with my cursor here? We have a, there you go. No, pencil. We have a simply supported beam, roller on one side, pinned on the other side, uniformly distributed like this, if I recall well. 50 kilonewton per meter on this side, 30 kilonewton per meter on the other side. Yeah, we already know by the pin support here, we have a reaction force vertically as well as horizontally. We have here reaction force only vertically. Horizontally, there's only one, so this one is equal to 0 that we can neglect. Yeah. How do we end up with a value for RA and RB? By taking the static equilibrium equations into account. But therefore, we're going to make a first simplification. So we're going to divide this distributed force in two. So what do you see appearing? You see a horizontally distributed force, which is equally to 30 kilonewton per meter along the entire length of the beam. And you see a rectangular appearing. Yeah. From the first part here, we know in the meantime that we can make a resultant force of 30 kilonewton multiplied by the length, and the length is equal to how much in this exercise? 2 meters, I guess. We have 60 kilonewton taking place in the middle of the beam. Yeah, but for this rectangular shape, it's a bit of a different story. Yeah, how can I change the color? No idea. So for this rectangular shape, we cannot say that the resultant force, which is, okay, rectangular, we all know base multiplied by height divided by 2. So it means is the length of the beam 2 meters multiplied by the height, and the height is here. Where is it located? Here. The height is here equal to how many? 50 minus 30, which is 20 kilonewton. So 20 kilonewton multiplied by 2 is 40, is indeed a resultant force, but it does not take place in the middle of the beam. Where does it take place for rectangular force? For rectangular force, you need to know that the center of gravity is positioned at 1/3 of the higher part. So it means here at 1/3. Yeah, 1/3 of the entire length. So this is 1/3 position of the length. And here we have the position, the length divided by 2. And now you can calculate easily RA and RB because you have a simplification with 2 point loads along the beam at specific locations. Yeah. And that you can calculate then. So what is 1/3 of the length? 1/3 of 2. The L multiplied by 2. This the length is 2. This is 2 multiplied by 2. So this is at 1 meter. So some of the moments around A should be equal to 0, which leads to what? The sum of all the moments. And the first moments is the 2 multiplied by 20, which is 40 kilonewton at a distance of 2/3. As a first moment, acting clockwise, so we take it as negative. The second moment that we encounter if we positioned at point A, yeah, is the 60 kilonewton multiplied by the arm 1 meter. 2 divided by 2 is 1. Huh? Clockwise, so negative. Counterclockwise is the last moment, meaning RB multiplied by the length, meaning 2 meters, equals 0. So you have one equation where you can deduct RB from. The same you do for the moments around B. So can somebody calculate for me what is the value of RB, please? And tell me what it is. I have it here, but I enforce you to make the exercise now, and that somebody can tell me what it is, please. That is R. Where did I put? Is that RB or RA? Tristan, Jules, did you calculate the opposite side, Rune? Okay. And what do you calculate for RA? You're sure you took A and B, not the opposite way? You're calculating this one, huh? And the other one? It's a correct value, huh? Because for me, it's RA, not RB. When you're located in A, you calculate B. When you're located in B, you calculate A. Can you explain again how you find the resultant force acting on 1/3 of the length of the basis? It's a triangular. You see, this is a triangular load. Yeah? And the force, the surface of this triangle is the base multiplied by the height divided by 2. The basis is the length of your beam, which is 2 meters. The height is the 50 kilonewton minus the 30, which is 20 kilonewton. Okay, Simon? Who has for RB 63.66 and a little? If you and for RA, indeed 43.335. Somebody who has the solution? Or not? To calculate R, that's what I'm asking you as well. Tristan, can you give me your equation? You calculate it, otherwise I'm wrong, eh? With the solution. 1 second, let me take my calculator. I didn't try it out yet. I assume that what I have here on my notes is correct, but perhaps I should make the calculation myself. Plus 60. Gedeeld door 2. Why not? Yeah. Okay, Tristan. What you need to do? Yeah. We position ourselves virtually here in RA. This is where we are located. And we are looking at all the moments acting upon the beam, and all those moments should be equal to 0. The first moment is this one, acting clockwise, and which is this force, 40 kilonewton at a distance of 1/3 of the length. Yeah, so it's 40 multiplied by 2 divided by 3. The other moment that you need to take into consideration is this one, the rectangular part. 30 multiplied by 2 is a rectangular surface at a distance of the half of the length. And then you have the last one to take into consideration, RB, acting this way, multiplied by this arm. Okay, let me take a brand new one. You see it now or not? 1 second. How do I erase and take a new one? What is this? No. Eraser. No, I want to erase everything. Yes, clear. Okay. So what do you have? The simplification. Yeah. 1 second. Drawing. The simplification is this. RA. You have RB. You have in the middle the rectangular part, which is 30 multiplied by 2 at 1 meter. RB is at 2 meters. This is 0 meters of the beam. And then you have here from the triangular part at 1/3, meaning the length of the beam divided by 3, 1/3 of the length. You have a force of, what did I tell you before? 20 kilonewton multiplied by 2 divided by 2. Yeah, that is a simplification of all the external forces acting upon the beam, of which 30 multiplied by 2 is the rectangular shaped one, and this is the triangular shaped part of the uniformly distributed load. You see this, Tristan? This you have, huh? I guess. Correct? Okay, now what do? You will position yourself here virtually in RA. And if you position yourself virtually in RA, you need to do the sum of all the moments, which should be equal to 0. So you take this moment, which is 40 kilonewton divided by 2 multiplied by this arm, 2/3. You have to take this moment into consideration at the length of 1 meter and a counteracting RB, which gives you an equation equal to 0 with one unknown, meaning RB. If you position yourself here and you look at all the moments acting upon the beam, then you get your equation for RB. Huh? You see that, Tristan? Okay, I see a yes appearing. So your solution, 43.33, is indeed RB. Yeah, correct. And then if you want to find the opposite way, you want to reason the opposite way when you are located virtually in point B, then you calculate RA. Yeah, correct, Tristan. Yeah, you always have to imagine yourself as a microbe in that spot of the beam, and you will calculate all the moments. Yeah, from that point onwards, and then you get your solutions. Yeah, Rune, you found the error. Why it's RA and not RB? Yes, okay, perfect. Joris as well, you found a solution that is RA and not RB? What you calculated was correct, but you just swapped A and B. Joris? Who was it? Nee, Jules. Jules? Okay, perfect. Good. So now we have a view over all the external forces. Yeah. So I can again take a new one. Clear. And we can calculate it again, or we can make a drawing again, but then take into account all the external forces with values. So we have here an RA at which is 43.335. At the end, we have an RB, which is 36.665. Yeah. What is now the question? I think that the question was, what are the shear forces and the bending moments in the middle of the beam? Yeah. So here at 1 meter, what are the shear forces and the bending moments? If you would take into consideration the simplification as we use for calculating RA and RB, you make a error. Why? That simplification simplified this load by two resultants, one taking place in the middle, the other at 1/3. Then you do something wrong, because at 1 meter location, when you're located here, you only have to take into consideration all the forces acting upon the beam on one side, only on this side, not all the forces. Yeah? That's what's happening here. At 1 meter, you need to counteract all the forces acting upon the beam up front. Or you look from the other side as well. You can choose which side you're looking from the right to the left or the left to the right. But you are the microbe in the middle, and you need to counteract from looking one side. You choose which one. It does not matter. It's up to you. Yeah. Now, to make my life easy, I use the right part to make my calculation. Why? Because you see here a nice rectangular shape and a nice triangular one. The other one is also easy, yeah? But now we are lacking time. So I try to finish in time. So what do? We will translate this one to a force taking place in the middle, which is how much? Which is 30 kilonewton over 1 meter, which is equals to 30 taking place here at 1.5 meter. Yeah. And we have another one here at this pot, 1/3 from the middle, which is equal to what? The length, which is 1 meter, multiplied by that respective height. Now it's easier because it's in the middle of a triangular, and it's 10 kilonewton. Yeah. Okay, how do you need to calculate this in case you're not aware of? But this is basic mathematics. Normally, I know I have to explain it to you, but it should not be part of what I need to explain. Yeah. But okay, I'll do it anyway. If you have a triangular, yeah, and this you need to remember, a triangular like this one, yeah, this has a height, let's call it b, small b, has a length, let's call it small a, yeah. Then this height at any part is of course in relation to what? In relation to this length, yeah. So we can call this x, we can call this a. So what do we say? The ratio of b over a equals ratio of a over x. So if you know this, then you know what this value should be. Yeah. Now it's easy because it's halfway, and this was 20, so halfway this should be 10. Yeah. But you can calculate it also just using this basic principle. Yeah. And so you can make like this any equation at a certain distance x. You can calculate the value y. Yeah. And this you will need to use, of course, in all the exercises that follow. Yeah. But this is things that you need to do at home. You practice at home. This is basic mathematics. Yeah. So if you will do the simplification and you want to calculate the shear force and the bending moments in the middle. Oh, wait, I have to be here. Yeah, that's why I prefer in a classroom rather than online, because I really do not like all these things, but okay, we'll have to. Yeah. So what do we see here? Our beam, we have an RB, we have our RA, we have here at 1/3, we have a force you will see of 5 kilonewton. If you calculate it correctly in the middle, you will have your 30 kilonewton. Yeah. And then again at 1 meter, if you look from here to there, the sum of all the forces is easy because RB we calculated before, 36.6 is 5. So meaning that your shear force here is the sum of all the forces you encounter, which is 36.665 minus 30 minus 5. And then you have your shear force value at 1 meter. What is the bending moment value of 1 meter? Force multiplied by arm. This multiplied by this arm. 30 multiplied by this arm. 5 kilonewton multiplied by 1/3 here, which is this arm. 0.333 because it's 1 meter. And 30 at 0.5 meter. And they will end up in your bending moment. And that's how you have to reason shear forces and bending moment calculations. And that's how I use the simplifications with those shapes, triangular, rectangular, and I try to make simplifications which are of course valid for what you need to calculate. Yeah, and that's your exercise number 5. And then you need to go to your Word document to see some similar exercises that you can calculate. I can try to do a share screen, but I don't know if I have the Word document here to help you out and to stipulate exactly what you need to do for next time. So we can start off with something new. We only build up. We only do new things. And I will treat, of course, all the exercises of which you had problems with. Speaks for itself. So I will do again a shared screen. I will stop this one. I will share my screen. Share. I should have opened the Word document. So what you need to read at home, yeah? You need to read the introduction, of course, which is a background knowledge, yeah? That explains you about the shear force and the bending moments. The introduction for the bending moments. What is a shear force? What is a bending moment? Yeah. So you will see the figures coming from the presentation. You will have them again only explained in wording. Yeah. So you can read it at your own pace. Huh? For those who missed out, you can read it all. You can see the supports, what they're like, all the loads you can encounter, and then you will see examples explained to you without figures, but in equation style. Yeah. And you see here as well examples of the diagrams of shear forces and bending moments, how it evolves in case of a point load. You have here the exercise of a concentrated load, which I want you to make at home. I want you to make and prepare for next week, exercise 1, 2, 3. Yeah, only if you have problems, if you indicate it to me, I will treat your problems. So you have to make them at home. Yeah. Then you will have here the uniformly distributed load explained in equations. Yeah. And then you have to make exercise 4 and 5. That is what I want you to do minimally. Yeah. I know you have other things to do as well, but that is a start. You will see completely at the back of this Word document additional exercises. 1 second. Additional exercise. That's all what we're going to treat in the future. The additional exercises start on page here. Additional exercises. Yeah. From exercise number 12, you can only calculate maximum permissible load. You're able to calculate A. Only A. B, you're not able to calculate yet. We didn't treat it yet. Yeah, it's a nice example. If you're able to calculate this, you know, this is an example of something more difficult than you will get on the exam, because you have to reason a little bit further. On the exam, it will be quite copy-paste of what we treat in class, but with different figures. Yeah, and what you see on the film, and you need to look at the film as well. What you can do too as you like is 13A. Again, only the A's. Not yet the B's because you're not able to solve it yet, but you can solve question A here. You can solve here again from question 14, question A, only the A's. Yeah? Yeah, B you can do it here as well. A and B is possible. The diagrams as well. Maximum bending moment you can calculate too, and you can do A, B, C, and D in this case from exercise number 14. Exercise number 15, you can make completely without any problem. Exercise 16, you can make as well if you like. Exercise 17, you can only make the part A, not the part B. It's not possible because you do not have the knowledge yet. 18, not yet. That's for the future. 19, you can make. Yeah. 20 as well, 21 as well, 22 as well, 23, 24, 25 you can make as well. Yeah. And there it stops, I think. 25 is a new one for those who followed the courses last year. Yeah. So you see, there's a lot you can do at home to practice. And that's what I'm asking you now. It's only the first step. We will do much more than this. Yeah. So just a simple beam calculations with point loads and uniformly distributed load is the first course and the first thing you need to practice at home. Yeah. If you're not able to do all exercises, no problem. Next module, if you indicate me, I will organize an extra session together, like a kind of a monitorat, as they call it, to guide you through exercises that you have difficulties with. Yeah, then we do it in class. But next week, I will continue with a new topic in a way, but it's similar to what we have seen. And I will start with solving your questions. Is that clear for you? Or do you have any question still? You will try to do it, try to solve it. Some people might say, oh, what is this here? A part of a beam with nothing happens. What is your shear force here at this part if you look from, if you're located here at this and you take only this part into consideration? It's zero, huh? There's no force. So there's no shear force in that part of the beam. There's no external force, so there's no bending moment. It's zero. Huh? If you go from here or look from here to there or there for this part only, if you take that into consideration. So the logic, if you follow the logic as I explained to you today, okay, it looks new, it looks more difficult, but in a way it's not. There's no shear force. There's no external force at that part. There's no bending moment because there's no external force if you consider left to your location as a microbe in your beam. Okay, I will send you the link to the movie as well because I didn't think I sent you the link to the movie. Yeah, it's in the updated version of the PPT, yes, but you don't have the updated version because it was added on recently. But I will give you the link of the PPT straight after now of the movie. Because the movie also helps you to solve the questions in case you have problems with the exercises. So look at the movie as well. Yeah. Okay. Questions so far? Not yet. The challenge, of course. Huh? That's why we are here, huh? To challenge you and to give you something to do. Okay. To all of you, ladies and gentlemen, I wish you a nice afternoon and good luck with all the exercises. And I'll see all your questions following next week in case you have questions. Good day to all of you. Bye bye.